point in us if I never know. If you're gonna leave, I'ma let you go. I'm tired of the pain. Go away. I'm tired with yesterday. Father.
Bienvenidos nuevamente. A continuación damos el paso al moderador, al ingeniero Carlos Jaime. Por favor, Carlos Jaime, te pido nos acompañes en este evento y presentes a Robert, que será parte de nuestros panelistas como expositores.
Okay, thank you, Francisco. Hello, everyone. Thank you one more time to be here in this edition of CARLA conference. For me, it's a pleasure to introduce Robert Henschel. Robert is researcher and professor of the University of Indiana. He is the director of research software and solutions in the research technology division. He holds master's degrees in computer science from Technische Universität Dresden in Germany, and has a strong background in high-performance computing. Henschel, on the other hand, leads teams to utilize IU's advanced civil infrastructure to provide scientific application to researchers at Indiana University and national partners. He is the responsibility of the Advanced Biomedical IT Core that provides support for computational research to the IU School of Medicine. And also Henschel is one of the partners, scientific partners of Sendio. This technical talk is about the Sendio solution. Sendio is one of the most important and most oldest company in open source at the world. And this year is the first year that Sendio had with us here in CARLA 2020. Thank you very much, Robert. Please, your time. Thank you.
Thank you so much for the introduction. Okay, I assume you can all see my screen here, so let me get going. I'm not a professor at Indiana University, just to be clear. I'm a director in the IT organization, and the rest of the introduction was correct. It is my role to provide support and applications for our supercomputing systems at the university and make them available to all of our researchers, faculty, and staff, and students as well. I'm going to talk a little bit about a project that we call the Research Desktop, which is one way how we make our supercomputer systems easier, make them available in an easier way for new users. I'll just talk a little bit about IU and what we do when it comes to supercomputing at IU, and then introduce the concept of the Research Desktop, and then give a little bit of an overview of how we implemented it at IU. So IU is it's Indiana University, not the University of Indiana. Indiana University is a large public university in the state of Indiana in the US. It's basically in the Midwest, a couple of hours driving south of Chicago, if you're familiar with where Chicago is. The university has two large campuses, one in Indianapolis and one in Bloomington. And each of those campuses has about 50,000 students. So it is a fairly large university with about a history of about 200 years. It is when it comes to classification, it is an R1 university, meaning there is a lot of research going on. So our systems are there both for the education of students and for research of faculty members. And we have a fairly large central IT organization that supports all those researchers. From a supercomputing side, we have a number of small to medium scale systems. Our biggest system currently is a Cray system with about 1,000 compute nodes for a total capacity of a petaflop, all of that in CPUs. And then we have a number of smaller systems for high throughput computing, and then also a GPU cluster. Our new system that will come online later this year is GPU based, about 6 petaflop in the new Cray Shasta architecture with AMD Rome processors and NVIDIA A100 GPUs. We also run a system for the National Sciences Foundation in the US for a national audience that is allocated through Exceed, which is a federation of HPC centers in the US called Jetstream, and that is a cloud system where researchers can use cloud technology to run their jobs. So let me introduce the concept of the research desktop. One thing that we're faced with at IU is that we're trying to make our supercomputing systems as generally available and as useful to a lot of different students in a lot of different disciplines as we can. So the university has promoted that mode of access for a number of years, and we are really evaluated by how many different users from how many different fields of science can we make those systems available to. So when a researcher looks at the IT infrastructure at the university, they immediately have a number of different options, right? So they can compute on their own desktop or laptop. They can do this on an iPad or Chromebook to a very limited extent. Some departments have their own servers. We have a Windows environment called IU Anywhere, which is basically a Citrix farm where people can run Windows applications. We have a VM-based infrastructure as a private cloud system, and then we have the HPC systems and Jetstream. So all of those systems are available free of charge to a large extent, free of charge to our users. So it's kind of hard for our users to make to decide where to run their workloads. At the same time, a lot of those systems are Windows-based, or at the very least offer a very graphical user interface to getting your computation done. So when you look at the history of supercomputing, right? Supercomputers have evolved over the last 50 years from machines that fill an entire room to very, very powerful machines that can fit into a single rack. What unfortunately has not really evolved is how you interact with supercomputers. So yes, today we have some science gateways, we have some applications that will make use of supercomputing systems in the background. But when new students or new users of supercomputing systems get started, they are normally confronted with an SSH shell, right? And in the past, that was very easy because text mode was also how you interacted with your own personal computer. But nowadays, students and also younger researchers are growing up in an environment where a command line is not really a thing anymore, right? You are living on a Windows desktop or a Mac OS desktop, and icons and drag and drop are the way how you interact with a computer. So telling new users that, okay, here's this command line environment, go ahead, make productive use of the system, is not necessarily a great start. So when you compare this, for example, to desktop computing, right? So in the past, desktop computing very much looked like supercomputing in the sense that you had a text mode environment and then you had some ASCII art interface, for example, for word processing. And then a graphical shell was developed. And nowadays, I think we're running Microsoft Word in the browser, right? And that goes for a lot of other applications like Google Spreadsheets and the Google suite of products as well. So there was a real evolution from on desktop computing that just hasn't really happened in the supercomputing world. So the users that are coming into the systems today are coming with a whole new set of skills than they came 10 or 20 years ago. So it is important for us to provide a platform that takes those users and helps them along from an environment that looks very different. At the same time, as an HPC center, we're somewhat competing with cloud providers. And I have to say, cloud providers do an excellent job when it comes to public relations and advertising. So they have really pushed us to offer a more convenient environment. So, and I think that gets me to the third point. We are now tasked with not just providing an efficient environment where people can use our hardware resources in an efficient way without wasting CPU cycles, but at the same time, we need to provide a somewhat convenient environment that users don't have to completely start from scratch learning how to interact with that environment. So there is a certain trade-off between what new users really want and what we offer them. And the concept that we've really embraced here is basically a remote desktop solution based on Linux, and which looks very similar to your Mac OS or your Windows desktop, and where you can get started, and then you can learn more and more about the environment. You can grow into a command line environment. You can grow into a batch-driven environment, but you can start with something that looks very similar to your desktop environment. So let's take a look at the research desktop. Basically, this is the way how traditional access to supercomputers works. You have a laptop, you have a desktop, or you have your own machine. You SSH into a login node on a cluster. You prepare your jobs, right, and you submit them to a batch system, Slurm, PBS Pro, batch systems like those. And then they run on a compute node in the background, and then you get an email at some point saying, hey, your job's done. Please look at the results. I think this works very well. It's a very efficient way of using the system. People who have grown up with this metaphor, no problem. I personally think everybody should use the system through a command shell, but to get new users into that mode, this is what we did in parallel. Basically, you can still come from your laptop, or you can come from an iPad or Chromebook. You come to a system that looks like a desktop. You can run applications right on those nodes with point and click. So you can double click on MATLAB, for example, or Console Multiphysics, or RStudio, or some of the other graphical applications. And they are running on a system with 256, 512 gigabytes of memory, 32, 48 cores. So they are running on a powerful machine, and you can get work done right on those nodes. At the same time, you can also submit your workload to the batch system. So you basically, you can start off running locally, and then as you grow more, as you need more resources, you can figure out how to use the batch system. But you do not immediately have to go to a command line environment. You do not immediately have to go to a batch-driven environment. So what does the remote desktop look like? Again, the concept of the research desktop is basically a remote desktop. You can get to it from a browser, any HTML5 capable browser, for example, on Windows, Linux, Mac OS, iOS, on iPhone and iPad, Android tablets, Android phones, can all get to this. Is it super convenient to interact with a desktop from your phone? Probably not. But is it enough to check in how a computation is going that you've started a while ago? Absolutely possible. So, and there are native clients available from Sandio as well for opening a connection from macOS, Windows, and Linux with a native application. So this is what the desktop looks like. We've customized it a little bit. We're using Mate as the windowing environment. So everything that people know from Windows or Mac OS is right there. You have folder icons that you can double click on, file browser will open, and you can browse the files in your home directory or in your scratch space on Lustre or GPFS or Panasas. So basically anything that you are familiar with from your desktop is here as well. You have icons for applications that you can double click and the application will open right up. We've also installed some convenience applications like Firefox. So normally we would not recommend people browse the web from a supercomputer, but sometimes you want to download an application, or you want to download a piece of code from a website. Having a web browser available is very useful in those circumstances. So we started with the concept in 2015. We've started with the free evaluation license that Sandio offers, which at that point in time allowed you to run up to 10 concurrent connections, which is very nice. And we did a competitive evaluation of what software to use, and in the end settled on ThinkLinc from Sandio because of the open source history of the company. And we've seen that the company was involved in some open source projects, and also generally has contributed very well to the open source community. So we've started evaluating ThinkLinc, and then in the middle of 2015 made it available to a number of beta users. We ran it as a closed beta, meaning by invitation only for 6 months, and then as an open beta for 2 years, and made it generally available as a service in 2017. That is a very long time, but we basically took our time there to make sure that we've tuned the service to really be useful for new users, right? The service was immediately useful for power users, but we wanted to make sure that we have the desktop right, we have the support mechanism right, so that we can really make the service available to new users in HPC systems. And then we, first of all, called it Karst Desktop, which was one of our supercomputers was called Karst, and we basically advertised it as the desktop version of the supercomputer. To make it more general, we transitioned it to calling it the Research Desktop 3 years after we started. The system has undergone a number of changes, so it is really a very successful service at the university. We've grown from 10 dedicated servers to 26. We've done an upgrade from Red Hat 6 to Red Hat 7. We'll soon do an upgrade to Red Hat 8. We've also gone from the really ancient GNOME 2 version to a very similar looking but nicely maintained version of Mate. We've done some custom development on the solution as well around rclone for cloud access. So when you look at rclone is a command line application that can interface with cloud storage solutions like Google Drive, AWS S3 buckets, Box, Dropbox, a number of online cloud storage systems. And by making that available, users can configure to some extent their own access to cloud storage systems, because this is what they do on their desktop, right? If you have your files in a cloud storage solution, then you also want to get to it from the research desktop. And then we've used an open source product called Sanity to build a few graphical tools that help people navigate the system. So Sanity allows you to run graphical dialogues from shell scripts, which allows you to easily ask a user a question, for example, or display a dialogue, which is much, much better than just doing that in a command line way. So, and then the biggest change was some time ago, we introduced the web interface. So when we started with the service in 2015, the web interface was available, but we chose not to make it available to our users. But we've in the meantime changed our mind because we have more and more users who are coming to us from iPads or Chromebooks. And currently Sandio does not offer an application for iOS or Android. So for those users to get to the research desktop, we advocated they use the HTML5 version of accessing the service. So one thing that I really want to stress is that we really customized the way that users experience the system, and we've really spent some time in customizing the desktop and the support infrastructure as well, so that it really feels as close to a desktop environment as you can make it. So we allow for long-running sessions, for example. So when you connect to the system, when you're on campus, and then you go home in the evening, you can disconnect from the session will continue running. So if you have MATLAB, for example, open and you're doing computation, you can disconnect from it, reconnect when you come home, and the MATLAB session will still be running. It will have made progress in the calculation in the meantime. We allow those sessions to run for up to 7 days. So users have to connect to their session every 7 days. And the idea here is clearly to give you an environment that you can run in for a long, long time. So we do maintenance on our machine once a month or once every 2 months. And we have a large number of users who have their same session open basically for 30 days or 60 days in the same environment. So you customize the environment once, and then you just use it, which is hugely successful because users can do this on the login nodes of the HPC systems with Screen, for example, but teaching new users how to use screen is a really hard task. However, telling users how to close an application and reopen it, and it automatically reconnects to the existing session is very, very easy. So some of the use cases for the system, of course, running mathematical and statistical applications like SAS, Stata, SPSS, running graphical applications in the HPC domain. Think of the Vampire performance analysis tools, Alinea Map, Total View debuggers. We're offering visualization tools like VMD, ParaView, not GPU accelerated right now, but doing just plain visualization. Client-server applications like COMSOL Multiphysics or the Schrödinger suite of products. Easy access for compilers. We have a number of mathematics professors who teach Fortran in their class, and they just want a system where they can go to, write a Fortran application, and immediately compile it with, for example, GNU Fortran, without having to tell users how to install a Fortran compiler on their laptops. And then a big part is facilitating collaboration. So, for example, we have a research team around Dr. Franco Pistilli, who has a number of collaborators all over the world, in Japan, South America, and Europe, and they will all connect to the same research desktop at IU, and then basically find the very same environment. So sharing a data set does not mean you have to transfer a data set across the Atlantic to the Pacific here, but you can basically leave the data set on the machine where the research desktop runs and everybody can see it, which makes collaboration much easier. They all can use the same application, same scripts in the same environment. This is just a slide with all the icons of some of the applications that we run. We offer Jupyter notebooks, we offer RStudio services, and I think those are one of the more popular applications that are running on the research desktop. So just as to finish this up and allow time for questions, providing an interactive environment, however, requires more babysitting for users. Users fundamentally have higher expectations towards an interactive environment than they have towards a batch-driven HPC system. So if we make something available that feels like a desktop, we also need to come up with a support infrastructure that allows people to get quick answers around those and to monitor the system much better than we monitor the standard HPC system. So here's just, we're doing monitoring on licenses, users, and number of sessions, which is a nice overall growth. You can also see some of our maintenance base, but it's just important for us to know how many licenses are in use, what's the total number of sessions on a daily basis, so we can see if the system needs more resources. We have specific charts in place where we look at how many batch jobs are submitted from the research desktop. So how do we help users grow into productive HPC users with batch jobs? So the idea clearly is to take users on the research desktop and help them move along into a batch-driven system, and a few others. So I think as a summary, I think standing up the research desktop was a really interesting project for us. It has helped us reach new users and make the HPC systems more interesting for students and faculty members that don't have a background in high-performance computing. And in general, working with Sandio was a great experience. They are nice to interact with. Even for us, dealing with a company in Sweden is 6 time zone. There's a 6-hour time difference between us and Sweden, but so far we've had no issues on the support side, and they really understand how the university environment works when it comes to pricing and helping users really use their service, customizing the service. So with this, thanks so much for your time. Time for questions.
Thank you very much, Robert. So we are open for the questions. We have one here from the social network. So what is the main opposition of concerns from the users to the use of this kind of desktop solutions?
the main concern from users?
Yes.
So the main concern that users had was actually to use the batch-driven system, not necessarily the desktop one. So I think we had a lot of users that had trouble using the standard way of how we make the HPC systems available. We have not gotten many concerns about the desktop environment. One thing that certainly is one concern for us is that we're offering it in a shared way, right? So we have a lot of users who share the same node. So we have a number of policies in place that protect one user from the other. But for example, if a node dies because of a hardware defect, then 10 users lose their desktop. And then we will send an email and say, we're very sorry that you lost your desktop, but here's what you can do to recover. So I think that's the major concern.
Okay. There are another one. What about the performance problems due to the large scale platform? For example, in more than 2 campus or 2 geographic sites behind them.
So I assume the question asks for the graphical performance, right? If I have a graphical application for multiple campuses, how does this affect performance? I have seen no performance issues specifically from multiple campuses. I've used the solution personally from Europe and also from Asia. And yes, I mean, you have sometimes you have 50, 100 millisecond latency, but if you are within the global research network, you hardly notice. So for me, it is the convenience of having one open environment that I can take with me wherever I go vastly outweighs the performance issues. And again, for us, from a graphical point of view, things like MATLAB or COMSOL multiphysics or even Firefox as a browser run very well in the solution. The solution uses compressed SSH and then VNC as the protocol in a compressed SSH session. So that works very well, even over long distances.
Okay, thank you. The other one, though, so that is the research desktop a free software for HPC system based on open source software like a Slurm scheduler?
Sorry, say that again.
Is the research desktop a free software for HPC system based on open source software like Slurm, for example?
No, the research desktop itself, we have implemented it using ThinkLinc from Sendio. That is not a free software. You could implement this yourself using VNC and SSH, which are both free software and open source. But there is a lot of infrastructure in the Sendio product to monitor users, figure out how many sessions are open, provide monitoring. That we decided to rather go with a product from Sendio to get us a little bit of the convenience for the administrators and for the users as well. Okay. And it's fairly reasonably priced, I have to say. One of the big reasons we went with Sendio is because pricing was very reasonable.
Okay, the other one. Why not the use of GPUs today?
So we are currently not using GPUs in the ThinkLinc and research desktop environment. However, there's a number of other universities that use the ThinkLinc product with both remote GPUs and GPUs in the nodes. You can do remote OpenGL, you can do OpenGL on the same nodes, and this will work very well. We don't have GPUs in our nodes, but that is certainly something that we're looking for in the future.
Okay. Another one from the social network. So how we can be part of the contributors for Sendio?
Sorry, say that again.
How we can be part of the contributors, of the people that contribute for Sendio?
You can, if you have suggestions or you have code contributions, by all means, you should just get in contact with Sendio. There is a, we have not contributed to the product ourselves, other than bug reports, which were then fixed by Sendio. But Sendio runs a public bug tracker, and you can see their development on that system, and I'm pretty sure they have an email address and a contact form as well.
Okay. So I think that this is all of the question. Okay, so thank you very much, Robert, for your presentation, your speech. I invite to the next demonstration of send you in the program the slots to have this presentation. So thank you one more time, Robert, and please stay here in the channel of the conference via Zoom or via YouTube or the Facebook channel. Thank you very much.
Muchas gracias, Carlos Jaime. Muchas gracias, Robert. A continuación, para continuar con el programa, invito a Alvaro de Ossa, quien moderará y presentará la siguiente ponencia de nuestro speaker, Shengxiang Yang. Adelante, por favor. Bienvenidos.
Buenos días. Muchas gracias, Francisco. Para mí es un honor presentarles al profesor doctor Xin Yang. El doctor Yang obtuvo su doctorado en Teoría del Control e Ingeniería de Control de la Universidad de Northeastern en China y es actualmente profesor y director del Centro de Inteligencia Computacional de la Universidad de Montfort en el Reino Unido. Él ha trabajado en áreas, en problemas asociados a métodos de inteligencia computacional, incluyendo computación evolutiva, redes neurales artificiales y su aplicación en problemas de la vida real. La charla de hoy del Dr. Yang trata acerca de la aplicación de métodos de Swarm Intelligence o a problemas de optimización dinámica. Antes de pasar el control o el micrófono al profesor Yang, les invito a poner las preguntas que tengan para el final de su presentación en la sección de preguntas y respuestas en el espacio de Zoom. Muchas gracias, Professor Yang. Let me just say a few words about you in English also. I was saying I introduced you to Professor Shengxiang Yang. He's currently a professor and the director of the Center for Computational Intelligence at the Montfort University in the United Kingdom. We're really pleased to have you here, Dr. Yang, and thank you very much for accepting our invitation. Please go on.
Okay, thank you. Can you hear me and see me?
Yes, perfect.
Good.
Thank you.
Okay, let me share my screen. Hello, everybody. Thanks for the organizers for giving me this chance to talk about my research. One of my research area, swarm intelligence for dynamic optimization problems. I'm Xin Yang from Montfort University in the UK. I here give my contact details in case somebody is interested in some topic and you may contact me. First, I would like to briefly introduce my research center, Center for Computational Intelligence. This center, the basic mission about this center is to develop fundamental theoretical and practical solutions to different problems using different computational intelligence methods. This center was established in 1995. It is an old center. I took over this center in 2013 after I joined the Montfort University in 2012. For the moment, we have about 16 academic staff and a number of research fellows and around 30 PhD students. Here, I want to mention every year we host a number of academic researchers, including PhD students, visiting students. So welcome if anybody is interested in visiting us. We are glad to host your visits. In terms of research topics, we cover different CI areas, including evolutionary computation, fuzzy systems, neural networks, data mining, robotics, and games. Okay. For funding, we received funding from UK research councils and EU research councils. As you may know, UK is leaving EU, so for the future, EU side may be cut down, but hopefully we will get more funding from the UK councils. And we also get funding from local government and industries. For research cooperation, we cooperate with different universities in the UK, USA, Spain, and China, and so on. And for teaching sides, we cover both. We cover all areas, all levels, including BSc level, MSc level, and doctor training level. Okay. So we have a specialized YouTube website. We have put some of our work on this website. Okay. So this is a brief introduction about the research center. For this talk, first I would like to briefly introduce the swarm intelligence, the concept of swarm intelligence. Then I will motivate the research area of using swarm intelligence for serving dynamic optimization problems. I will briefly describe this concept. Okay. Then I will discuss some detailed techniques used by swarm intelligence for serving dynamic optimization problems. After that, I will show some case studies, okay, in this area, and then we will briefly discuss the challenges we're facing in this area and the future directions for this area. Okay. So that's about the structure of the talk. So as you may know, swarm intelligence, in fact, there is no, how to say, standard definition or everybody accepted definition. Okay, for swarm intelligence, we can say intelligence achieved by collective behaviors of different individuals. Okay, or we may say a swarm of agents. Okay, usually for a system, it consists of a number of agents. These agents interact with each other, okay, interact with each other locally, and they also interact with the environment. For each agent, it follows a very simple rules. Okay, so these simple rules usually involve self-learning or social learning from each other, and through these simple rules, agents carry out interaction with each other, and as a whole, as a swarm, eventually there will be emergence of intelligent global behavior. Okay, and this intelligent global behavior, sometimes it may be unknown to the individual agent. Okay, but from the swarm level, from the whole global level, there will be some intelligence appear. And so that's the basic concept of swarm intelligence. In nature and in biology, we have many such examples. For example, for fish and for birds and for sheep and so on. Okay, they all show some swarm intelligence through collective behavior. And from our computer scientists, for optimization computer scientists, we borrow ideas from swarm intelligence. Okay, and we develop swarm intelligence algorithms. This encapsulates a class of optimization algorithms. Okay, there are different algorithms developed. Here I list some major swarm intelligence algorithms for optimization. Okay, for example, we have particle swarm optimization, we have ant colony optimization, and artificial bee colony algorithms, ABC, and we have bacterial foraging optimization, BFO, and so on. Okay, five flyer algorithm, and so on. Okay, there are some more. Okay, in this area. Here, I want to briefly introduce the two. One is particle swarm optimization. It was developed in 1995 by Kennedy and Upperhut. Okay, so the basic idea is a population. It is a population-based optimization methods. So it was inspired. Let me minimize this. It was inspired by social behavior of bird flocking or fish schooling. Okay, and swarm members can profit from their own discovery and previous experience of other neighbors. Okay, so for each member in the swarm, during the searching process, it will learn from its history. Okay, and it will also learn from its neighbor's history. So that's the basic idea of particle swarm optimization. Okay. In terms of algorithm size, PSO consists of a swarm of particles. For each particle, we record two things. Each particle has its position. Okay, so its location in the search space. Another thing is the particle flies through the search space with a velocity. So each particle has these two major things recorded: position and velocity. And the velocity of each particle is influenced by three parts. Okay, as this formula shows, okay, Vi is the velocity of particle I. It is updated according to three parts. The first part is previous velocity. Okay, this part shows the momentum factor, and the second part is the cognitive component. It shows for each particle it learns from its own experience. Okay, its own experience. Here. If we look further here, for the second part, this is a random number, okay, random number, and the PI is the best position learned during the history for particle I. Okay, so we use this, take this difference, try to learn, make a particle I to learn from its own history. Okay, the third part of this formula shows the social components. Okay, so each particle learns to its neighbor's best position found so far. So this GI is the best location or solution found by the neighbors of particle I. Okay, so this is the velocity update formula, and then the position of particle I is updated using this velocity. Okay, so this is the basic formula, basic principle for particle swarm optimization. Okay, for the second algorithm, we want to briefly introduce ant colony optimization. Okay, for real ants. In fact, as you may know, for real ants, different ants communicate with each other by using pheromone. Okay, somebody, Wilson did this experiment in 1962. So we have the list and we have the food. Okay, and there are passes between the list and the food. And we put the ants in the list. Eventually, the ants will follow different routes to find the food. Okay, and when the ant found the food, it will go back to the list. Meanwhile, it will lay some pheromones over the path it used, and this pheromone will guide the following ants to find the path towards the food. Okay. Eventually, through this method, the shortest path will accumulate quite a lot of pheromone and will be used by the following ants. So that's the basic idea of finding shortest path by the real ant colony. And for ant colony optimization, we borrow the ideas from real ants. Okay, we mimic the behavior. Okay, it was developed in 1996. Okay? So for ant colony optimization algorithm, it usually we solve optimization problems using graph. Okay, and we initially we put equal amount of pheromones on all the edges. Okay, all the edges, and we let ants to find solutions from the list. We put ants in the list. Okay, we try to find the solution to the destination, and we put ants in the list and let them make decisions step by step to find the full path to the destination. Okay, and when the ant find a path, when it will go back to the list and update the pheromone on the edges used, and eventually the shorter path will have more and more pheromones accumulated. Okay, so this is the ant colony optimization algorithm, the basic idea. So here we involve forward mode is the path construction mode. In path construction, for an edge, suppose this is an I and the case edge. Okay, suppose this is the case edge. Now it's in at node I. It needs to make decision to select the next node. Okay, so the edge make decision according to this probability, Pijk. So we can this probability consists of two parts. First part is tall Ij. So this tall Ij is the existing pheromone trail value, okay, between these two nodes, or okay, on the edge Ij. And the second part is eta Ij. This is the heuristics information. In this example, eta Ij may be the length of the edge. Okay, so the edge make decision to select the next node according to this probability, and the edge will find a full solution step by step using this formula. And when the edge finished the solution construction, it may update the pheromone trails, the edges used by the edge using such formula. Okay, it will deposit pheromone on those edges used in the tools. Okay, in the tool. Okay, this is one pheromone update rule. Another rule is evaporation. Okay, for each edge, the pheromone amount will decrease according to this formula. Here, rule is called the evaporation rate. Okay, evaporation rate. So this evaporation rule means reducing the pheromone trail for each edge. Okay, so this helps. In fact, this is also happening for real ant colony. Okay, in SEO algorithms, we have this. It will help us to forget bad decisions made before. Okay, so that's the SAO algorithm, basic ideas for SAO algorithm. For the moment, for swarm intelligence algorithms, they have been used in different fields, okay, because of their advantages. For SI algorithm, we can involve multiple solutions. We can get multiple solutions in a single run, and we don't require the problems to be solved have special features. Okay, so they're usually easy to use. Okay, because of that, nowadays they have been used in different fields. I here just list some typical fields. Okay. Now let's motivate dynamic optimization problems. Traditionally, for SI research, they are focused on stationary problems. Stationary problem means the problems are given, then the problem that does not change. Okay, for stationary problems, our aim is to design SI methods that can quickly find the optimal solution and precisely find the optimal solution in the such space. I use this figure to show the basic idea. Okay, suppose we use this rectangle to show the such space. Okay, and this red point, I mean, to denote the optimal solution in the such space that we want to find. Okay, usually for SI methods, we start from a population of random solutions. Okay, random solutions as shown in this by this white points. Okay, and through the searching process, eventually we will converge the population of solutions towards the red point, towards the optimal solution. Okay, that's for a stationary problem. That's what we wanna do. We wanna find the optimal solution quickly and precisely. Okay, but for many real-world problems, in fact, we involve changing conditions. We're facing dynamic optimization problems where changes occur over time. A typical example would be in the transportation systems. Okay, so for all transportation systems, the travel time between two nodes may change over time. Okay, we usually don't have fixed travel time between two nodes. Okay, so what are dynamic optimization problems? Here, I give a brief description. It's not a definition. Okay, it's not a strict definition. Okay, in general terms, we say optimization problems that involve change over time. So these problems are called dynamic problems, or sometimes we call time-dependent problems. Okay, if we want to use formula, then we have this objective function. It involves the t variable. So this is the time variable. Okay, because the formula may also involve the decision variable. X is the decision variable. Okay, and S may be some system parameters. Okay, so for dynamic optimization problems, the key things is we introduce this time variable into the problem. So for DOPs, there are special class of dynamic problems that are solved online by an algorithm as time goes by. So in other words, when an algorithm is solving a problem, the problem may change at the same time. And so for this kind of problems, we call them dynamic optimization problems. So why dynamic optimization? Why should we study dynamic optimization problems? Okay, because they bring in new challenges to SI methods. For dynamic optimization problems, because the problem changes over time, so the optimal solutions may also change over time in the search space. So we need to track the moving optimum over time. As this figure shows, okay, time points, the optimal solution is here in the search space, and the population of solutions may sort of converge towards the optimal solution. Okay, but if now the problem changes, the optimal solution may jump to another space, another place in the such space. Now, the algorithm will face problem because the population of solutions are sort of converged. Then it will be difficult for the converged populations to follow the new optimal solution. Okay, so that's the fundamental challenge for dynamic optimization problems for swarm intelligent algorithms. So why should we study SI to solve this kind of problems? There are two reasons. First reason is many real-world problems are dynamic optimization problems. So we need to face them. We need to present solutions to decision makers over time. Okay, we need to track the problem. And the second reason, as I mentioned, for SI methods, we borrow ideas from swarm intelligence in nature, in biology. As we know, in nature, we always face changing conditions. We always face dynamic environments. Okay, so in nature, in biology, there should be some rules, some principles to deal with dynamic optimization, dynamic environments. Okay, so if we learn from biological evolution, biological behavior, we can borrow those principles to enhance SI methods, SI algorithms to deal with changing conditions. And so that's the reason, important reason why we should study SI methods to address DOPs. And this research area is now rise quickly in recent years. Okay. Now let's see if we want to use SI to address dynamic optimization problems, what we should do. So there are two things we need to consider, we need to do. First is we need to detect potential changes. Okay. So sometimes only when we know the problem changes, we take corresponding actions to address the change. That would be great. So if we can detect the problem changes, that would be great. Of course, here we involve whether we can be successful to detect change and whether how much effort, how much cost we should use to detect change. Okay. So this is the first thing to do. And when we detect change, then we need to take actions to track the change. Okay, to track especially track the changing optimal solutions. Okay, and usually we expect the algorithm to have a steady and fast change response. Okay. And of course, when we try to track the changing optimal, we try to reduce the cost. Okay. So there are two things to do. Okay. For changing detecting change, I want to briefly say something here. There are two ways to detect changes. First way is to use individuals. We call it individual level detection. Okay. The second way is to use the population level information to detect change. Okay. There are two ways to detect change. Here I want to mention for both methods, we cannot guarantee we can detect change. Okay. For example, for the individual level detection, usually the idea is we can re-evaluate the objective functions, objective values of some selected individuals. We select some individuals from the population to re-evaluate the fitness. If the fitness changes, okay, then it means that the problem changed. Okay. Of course, whether it is successful or not depends on the selected individuals. Like this figure shows, if the problem changes, the change of the problem involves this area of this part of the search space, and the individuals we selected for re-evaluation fall in this area, then we can detect the change. Okay, we can detect the change because before for two re-evaluation, the values will change, fitness value will change. But if we the selected individuals are in this area, that does not change. Okay, that does not change, then we will not be able to detect the change. Okay, because the fitness will not change of these selected individuals. For population level detection, we can use some statistical information of the population to detect whether the problem changed. And like this figure shows, if before a change, we find the statistical the distribution of individuals in the population like this. Okay, and after generating, if we find that the individuals are distributed like this, so the distribution of individuals changed significantly, then usually this is because the problem changed. Okay, for SI algorithms, usually for population level information, statistical information, usually they move smoothly. Okay, change smoothly. If we involve significant change, that's mainly because the problem changed. Okay, that's the idea of population level change detection. Okay, so if we detect that the problem has changed, then we need to take actions. Okay, response approach. How to respond to change? This is how about restarting an SI algorithm after a change? This is a very easily asked question. Okay, so if we detect the problem changed, we can restart the algorithm. Okay. In fact, this idea, restarting idea, it is a natural and easy choice. Okay, it's easy to do that. And in some special cases, special dynamic cases, restarting an algorithm may be a good choice. Maybe a good choice. Okay? It happens, but in most cases, it's not good choice because of two reasons. First, if we restart an algorithm, that means we get rid of all information before. Okay, all knowledge we learned before. So this will waste the computational resource, and this is inefficient. Okay, this is one reason why restarting is not good. Another important reason is that because SI methods usually they involve stochastic rules. If we restart SI algorithm, we may lead to different solutions. Okay, we may have very different solutions before and after a change. Okay, technically it's fine, but in reality, if the solutions are quite different before and after a change, it may involve many real-world problems. Okay, for example, for the transportation system, before a change, the driver run the vehicle between city A and city B. Okay, after a change, no matter how significant the change is, if we restart the algorithm, then we may finally reach a solution. Ask the driver to run between city A and city C. Okay, city A and city C. This will involve practical problems. Okay. So because of our reasons, it's better to have extra response approaches to deal with dynamic optimization problems. Okay, to enhance SI algorithms performance for dynamic optimization problems. Over the years, there were different extra approaches developed. Typical approaches can be divided into 4 kinds. We can use memory, diversity, multi-population, and hybridization methods to enhance SI's performance to deal with DOPs. Okay. We have published a survey paper recently. Okay, in this paper, it gives details for different kinds of methods. Here, I want to briefly introduce these 4 kinds of methods. First, memory-based approaches. For some DOPs, they are cyclic. Okay, so it means even though the problems changes over time and the optimal solutions also changes over time in the search space, but after certain changes, for example, in this example, after 5 changes, the problem will come back to its original state. Okay, for this kind of problem, for this kind of cyclic DOPs, we may use memory to store and reuse information to help the algorithm to track the changing optimal quickly. Okay. For example, like this figure shows, during the searching process, we may store solutions like this blue points shows. We may store solutions. Okay, these blue points into the memory. Okay, now if the problem changes, if the optimal solution jumps from this place to the next location, and we can re-evaluate the blue point, and we can find maybe this point stored solution may be very close or at the same place of this new optimal solution. Then we can use that stored solution to track the population of solutions quickly to the new optimal solution. So this is the idea of the memory schemes. Okay. Of course, how to implement memory schemes, and we have several questions. What information should we store in the memory? Okay. Usually we can store the current based individuals in the population into the memory. And when the problem changes, we can merge the memory solutions with the main population solutions. Okay, that's the first question. The second question is when and how to retrieve memory. Usually this memory space is limited. So when it is full, how do we update this memory? So this is a question we need to consider. And how to update memory. I have mentioned that. When and how to retrieve memory. The second question is when and how to retrieve memory. So usually when we detect the problem change, we can use this memory. Okay, so there are several questions to consider. The second kind of method is called diversity-based approach. Okay, for this approach, we have two sub classes. One is diversity increase. The basic idea is for the main loop of the algorithm, which we have this detection change. If we detect the problem change, then we increase the population diversity temporarily. Okay. For example, we may use put some random solutions into the population to increase the diversity of the population. So this is a diversity increase scheme. We may also use diversity maintenance scheme. The idea is that in the main loop of the algorithm, for each generation, for each iteration, we can insert some random solutions into the main population. Okay, we can call them random immigrants. Okay, the basic idea is to avoid the population to converge to a location in the search space. Okay. This is the diversity-based approach. The third kind of approach is we call it the multi-population approach. The idea is we divide the search space by using different populations, subpopulations. For example, in this example, we have 4 subpopulations, okay, created in the 4 search space. And each subpopulation will search in its local area. We design some rules to avoid the different subpopulations to overlap in the same area. Okay, Now for multi-populations schemes, for example, at some time points, the optimal solution may be in POP3's area, then POP3 will take the major effect, okay, to search for this optimal solution. If at some time points, the problem changes and the optimal solution jumps from the POP3's area into another place, okay, into the new place. This new place falls in POP1's area, then POP1 will take action, becomes the major POP to track the new optimal solution, So that's the idea of multi-population. It's mainly a divider control methods. Okay? The fourth kind of approach is called prediction approach. For some dynamic optimization problems, sorry, here should be DOP. Okay, for some dynamic optimization problems, the problem changes, but it follows some predictable patterns. For example, where the problem changes and when the problem changes, there may be some predictable patterns inside the changing conditions. Then for this kind of problem, we can use some prediction methods to predict where the problem will change and when the problem will change. And then before the problem really change, we take some actions, pre-actions to prepare the population. And when the problem really changes, because the population has been prepared, we can immediately track the new optimal solution quickly. So that's the basic idea of prediction approach. Of course, here, what prediction techniques we can use? There are different choices. Okay, in the literature, there are different choices, different prediction techniques used to enhance SI algorithms to track the moving optimal solutions, the changing conditions. So another kind of method is a hybridization approach. The basic idea is to use hybridization technique to improve the performance of SI methods to address DOPs. Here, we can hybridize SI with, for example, local search method or diversity schemes. Okay, there are different choices. The second idea is we can hybridize SI method with other meta-heuristics methods. Okay, combining the strengths of different meta-heuristics methods. Okay, for example, PSO plus cellular automation, and the PSO plus fuzzy C means, and so on. Okay, there are different choices, different hybridization methods in the literature. So, as I mentioned, there are different kinds of approaches to enhance SI's performance to address DOPs. Here, there is no clean winner among these approaches, because different approaches are good for different dynamic situations. Okay, for memory scheme is efficient for cyclic DOPs. If the problems return to its original states, for such problems, memory schemes is good. Multi-population schemes, they are good for multimodal problems. So if the problem involves different local optimal and global optimal, and this local and global optimal solutions, they compete with each other over time to become the global optimal solution, then multi-population technique is good. Okay, time runs, so I need to be quick. And diversity schemes are usually good because they avoid the population to converge. Okay. Here, guiding rule is how to balance the exploration and the exploitation capacity of the solution of the algorithm, okay, to track the optimal solution, the changing optimal solution. Next, we use a few case studies to introduce how to solve problems. Okay, and recently we developed a multi-swarm particle swarm optimization algorithm to address continuous DOPs. The basic idea is we use some clustering techniques. Very simple. It's called single linkage hierarchical clustering technique. We use some clustering techniques to cluster different individuals in the population into different subswarms, subpopulations, and let each subswarm such one peak in the landscape, in the fitness landscape. Okay, and we use some techniques to avoid different populations, subpopulations to overcrowd with each other. Okay, and also we designed an adaptive method to create a proper number of subpopulations in the such space. Okay, so this is the basic ideas of this multi-swarm particle swarm optimization algorithm for addressing continuous DOPs. I have a demo here. Let me show this. I don't know whether you can see this. Let me reshare. Okay. And let me. Pause share this. Stop share this, and let me share the. Okay. Let me reshare this. Okay, let me reshare this demo. Okay. Okay, I don't know whether you can see this demo. So in the fitness landscape, we have multiple peaks. Okay, multiple peaks. Each peak has its location, its height, its slope, and each peak can change regarding such these features. Okay, so you can see over time we have changing peaks inside the fitness landscape. Our aim is to try to track as many peaks as possible and find the highest peak, the global peak over time. Okay, here you can see the problem changes over time, and for our algorithm, here we use clustering techniques to create different populations, subpopulations over time, and each subpopulation we tried to let the subpopulation track one peak. Okay, so you can see over time the algorithm creates different subpopulations. Okay, and try to track the changing peaks and find the global peaks, global peak over time. Okay, so this is a demo for multi-swarm technique. Let me stop this and go back to the slides. Okay, that's for continuous DOPs. The second case study is we try to use at-colony optimization to solve combinatorial dynamic optimization problems. Okay, so this is the problem is dynamic railway platform reallocation problem. As you may know, for railway systems, usually the rail timetable was decided half a year or even long ago. Okay, but in reality, there may be different changes or different conditions happens. So some trains may arrive late at a station according to its original schedule. Okay, and if a train arrived late, it may affect the following trains in the timetable, in the network. Okay, we may have such called knock-on effects. Okay, so multiple trains may be delayed in succession. Each new delay changes the problem. So for this DRPRP problem, we try to reallocate multiple successive delayed trains to new time slots. Okay, and also to maybe different railway platforms. Our aim is to minimize the ongoing delay in the whole system. Okay, we want to minimize the delay in the whole system. So for this research, in fact, this is an EPSRC grant research. We cooperate with the railway network rail in the UK. We use Leicester railway station as an example to study this problem. For Leicester railway station, we have 4 platforms, and each platform is bidirectional. It means the trains can arrive from 2 directions through this for each platform. Okay, for each platform. So we have such layout of 4 platforms for Leicester railway station. For this research, we use a network of a railway system. Okay, we use a Leicester railway station, put Leicester railway station at the center, and we include 50 miles of the network. Okay, and take this as our system. So inside this network, we have totally 225 time points. Okay, time points in this network, and then we extract the timetables from the public available ITPS system. Okay, this is what we extracted from the ITPS system, and it's the timetable. Okay, it's chaos, but if you understand the meaning of each row, then eventually we can extract the timetable for each train to pass the network. And we developed the simulator. Okay, Leicester station simulator. I can show this simulator. By the way, I want to check whether you can hear me and you can see my screen clearly.
Yes, we can. Thank you.
Oh, that's good. Okay, so this is the simulator. So we extract that timetable information from the ITPS system and use Leicester railway station to carry out this simulator. You can see trains coming and passing different platforms from both directions. Okay, and based on this simulator, we carry out research regarding the dynamic railway platform reallocation problem. Okay. Here we use at-colony system, the max-min at system. So this is one SEO algorithm to solve the problem. Okay, to solve the problem. And when in this problem, when at try to construct a solution, we do this way. We let all ants start from a dummy node 0, and then let each ant to decide which node to follow. So here, the each node in the graph represents a train at the platform assigned to the train. Okay, so each node consists of two information. One is which the train involved, and the other is the platform selected for that train. For example, this node is train A using platform 1. Okay, so the ads make decisions like this: go to one of these nodes and then make another decision, go to the following nodes, and so on until all the trains are decided, assigned to different platforms. Okay, to different platforms in the railway, in next railway station. Then we construct a full solution. Okay, so this is how we can represent a solution, or how an ad construct a solution, okay, using such a network, such format. And as I mentioned, we may involve changes, dynamic change. Here, dynamic change maybe means a train may be delayed or something like that. If we, after a dynamic change, then when we use this network to construct solutions, if the train has passed the railway station, then that train will be taken away from the network. And if there are new trains arriving to the system, to the network, then it will be added to the network, and then adds using the same idea to construct a solution. Okay, so that's how to deal with a change when we construct a solution. Here, I want to mention one thing. We try to avoid unnecessary platform reallocation, especially I come back to this layout. For next railway station, for this platform 3 and platform 4, they are together. So the passengers need not to go over the bridges to reach platform 1 and platform 2. So platform 1, platform 2, they are together. Platform 3 and 4, they are together. But 1 and 2, they are away from 3 and 4. We need to pass a bridge to reach the other side. So when we let ads construct solutions, we take into account the layout of different platforms. We try to avoid reallocate a train from platform 3 to one of these, or from platform 1 or 2 to the other side, to avoid passengers passing the bridges. Okay, so we take this into account in the heuristics information in the SEO algorithms, and then we carry out experiments to compare our algorithms with it's called first free platform method used by the scheduler. Okay, and for details, please see the paper, and this is the result. So our method is much better than the current first free platform method used by the scheduler. Okay. Okay, time is so quick. So this is another case study. Due to time, I skipped this third case study. So this is for dynamic multi-objective optimization problems. We involve two objectives. First, minimize timetable deviation. The second is to minimize additional energy expenditure. So this is for scheduling rescheduling trains to pass this. We call it junction, double junction. Okay, double junction. And due to time, I don't want to go to the details. Anyway, we use SU algorithm and plus some enhanced techniques to address the problem, and we compared the performance, and our methods improves the situation. Okay. And for this area, some challenging issues we are facing for the moment. Challenging issues. First is detection changes. Okay, so for many researchers, they assume it's easy to detect problem changes, but in fact, in many DOPs, it's not easy to detect changes. So we need to consider efficient detection techniques, or we need to develop algorithms that are not based on the change detection. Okay. The second challenge is to understand the characteristics of DOPs. So what features makes DOPs easy or difficult to solve by SI methods? Okay, so there is very little work in this area. We need much more effort to understand this. And the third challenge is to analyze the behavior of SI method when serving DOPs. So we also need more theoretical analysis tools and works in this area. Here, the big question is which SI methods to solve what DOPs. This question is easy to ask, but difficult to answer. The biggest question. Okay. The fourth challenge is real-world applications. When we try to use SI methods to address real-world DOPs, we need to consider how to model real-world problems. This is a challenging question. And the second question is how to extend the SI methods to address modeled DOPs in the real world. Okay, these are challenging issues we face. For future works in this area, this is a growing area, but it's far from well studied. We need different methods. Okay, develop different methods to address DOPs. We need to carry out theoretical analysis, and we need to address more challenging problems. For example, dynamic multi-objective optimization problems. And for real-world applications, works are greatly needed. It may involve different areas. I put some areas here, typical areas here. It may involve other areas. To summarize, using an SI to address DOPs is an interesting and important area. This domain is still young and very active. We need to take actions to address more challenges in this area. And more young researchers are required, are needed to enter this area. And I put some information here. Okay, thanks for your time. Thanks. Sorry, I overrun a little bit.
No problem. Thank you very much, Xin Yang. We are just a little bit off time, so we'll take one question, and I will ask you, if possible, later to reply to the questions there on the question and answer section in Zoom. So maybe you can reply to them in written. Is that okay?
Yeah, okay.
Thank you. One of the questions asked here is, what is the, what I would like to address now, what is the memory impact if you change scale in the swarm intelligence model?
Sorry, what is the memory's impact?
So if you change the scale of your problem, the size of your problem, the number of individuals, or the number of the number of vertices, how does that impact memory requirements?
Okay, that's a very interesting question. In fact, I did not consider this question before, but even though the size of problem changes, but for the original size problem, So if it is cyclically changing, memory scheme also works for that. And I think memory schemes will help, even though you increase the size of the problem, because by memorizing things relevant to your sub-problems, yeah, I can say if you increase the size of your problem, but for the original size problem, it may be taken as the sub-problem of your problem. Yeah, so memory will help that sub-problem, and then I think it will also help the changing problem, a bigger size problem.
I see.
Yeah.
Thank you. So I'm sorry we're out of time. So you can see the questions in the Q&A section, and okay. I would appreciate if you can reply to that later. Okay. Thank you.
Okay. Thanks. There are many types of SI algorithm. How can we decide what is the best for a particular problem? This is an interesting question. This is also a challenging question. It's difficult to say which method to use for your particular problem. We need to start from your particular problem. We need to analyze your particular problem. For example, if it is a continuous problem, or whether it is a combinatorial problem, for different kinds of problem and a different features problem, we may how to say, map back to the algorithm side. For example, SO may be good for combinatorial problems, and PSO may be good for continuous problems. It depends on your problem features. There is no sure answer to that question, but by analyzing your problem features, it may help you to decide which method, which algorithm to use. Second question, okay. How different could be the final solution to a given time t if we restart
Professor Yang?
Yes.
The moderator asked you to answer the questions in writing. We're well over the time, and there's another speaker waiting.
Okay. Okay. Thank you. Thank you. So due to time, I don't have time to answer each questions. But if you are interested in any part, you can email me. Okay, you can email me. Then I will communicate. Try to answer the questions.
Okay. Thank you very much, Shengxiang, for your acceptance of participating. It was really interesting. Thank you.
Thank you. Thank you. Thanks for all your time.
Thank you so much, Dr. Xin Yang. Y muchas gracias a nuestro moderador, el Dr. Alvaro de la Ossa. Continuando con el programa, invito al Dr. Carlos Jaime Barrios, quien va a presentar la siguiente ponencia, el caso de estudio de nuestro sponsor, ThinkLinc. Por favor, ingeniero Carlos Jaime, si es que nos puede confirmar.
Yes, thank you very much, Francisco. So, what a pleasure to present Henrik Villar by the side of Zendio. Henry is one of the developers and Linux administration and DevOps of this company. And Henrik shared with us the different case of SUD that is made by Zendio ThinkLinc, this important tool that maybe here in Latin America we are very interested. Henrik is his institute was in the Open University and BGC in open development, and a master's degree in the Birkbeck University of London in computer science. So thank you very much, Henrik, and please.
Thank you. Okay, let me try to share the screen to see if that works.
Mm-hmm.
Cool. Can everyone see this?
Yes, perfect.
Okay, great. Okay, so I don't actually work for Zendio. I work for a company called Man Group, but we run a lot of ThinkLinc clients. So I will talk you through our little setup and how it works. So first of all, Man Group is an active investment management firm. We have $108 billion under management at the moment. We run mainly quant strategies, i.e. we write software that makes trading decisions for us. Man Group itself consists of 5 hedge funds, and we have presence in 4 continents, and we employ roughly 400 researchers and technologists. And basically everything we write is written in Python, apart from some very time-sensitive things that we use C for and Java. And everyone who works for Man Group really knows at least a little bit of Python, including people who wouldn't necessarily be in technology. So myself then, I'm a staff engineer in the quant infrastructure team at Man Alpha Tech. So Alpha Tech is a subdivision of Man Group, of course. I've been working with Linux and other Unixes for more than 20 years now. And as the presenter mentioned earlier, my latest educational experience is an advanced computer science MSc from Birkbeck University in London. My current interests at work are mainly focused around automation and around Kubernetes. And in the automation space, I mainly play around in Ansible at the moment, although because I'm an old Unix person, I still use a lot of Bash, and we also write a lot of Python to automate simple things. So anyway, so our tech stack then at Man Alpha, the hardware-wise, we run a large estate of HP and Supermicro machines. We have about 6,000 cores in total and about 75 terabytes of RAM for our researchers. Storage-wise, we have, of course, local SSD in all the machines, but we also run flash array and flash blade technologies from Pure Storage. The flash blade in particular is great. We get S3 and NFS through the flash blade, and it handles as many IOPS as we have ever managed to throw at it, including running large Spark simulations. So we regularly read and write more than 15 gigabytes per second to it. For virtualization, we use OpenStack and VMware. Primarily VMware would be used in pre-production and production, and OpenStack on the development and research side. And the way we provision compute to our users is that everyone gets their own virtual machine in OpenStack, and they run a Linux desktop in there, which we then serve to the user using ThinkLinc. So as a user at Man, you would typically run all your strategies and simulations would be done in Kubernetes or run on Docker on bare metal, or indeed in bare VM, as it were. All our new development now goes into Docker containers so that we can easily migrate workloads between, well, different clusters, first of all, but also DR and those kind of things become really simple because we can move like a lump of software and everything just works exactly the same. For data storage, we use a lot of MongoDB because it seems to be one of the fastest platforms we can get at the moment. We've also written our own tick store where we store financial ticks from markets. It's called ArcTick and it's open source. It has quite a large user base by now, not just Man Group, but other financial organizations also use that. And then we have a list of sort of usual suspects that you would expect to find in sort of the quant type companies. So we have Spark, of course, we run Jupyter notebooks, a bunch of Jenkins for builds and ad hoc jobs, and we also write a lot of custom in-house software, as I mentioned, in Python. And I think I mentioned already that all our strategies and all our research is developed in Python. Yeah, so the way that would work then is that a researcher would play with data in Mongo and ArcTick, and they would come up with a strategy that works, and then a developer would take that Python code and basically productionize it so that it runs properly in production and is unit tested, etc. On the quant infrastructure side, we have, like mentioned earlier, we have a lot of servers, but there's actually only 5 full-time Linux engineers at the moment. So we have a small team and we have lots of servers spread across a large geographical area. And we also have lots of users that we also support. So we need decent automation tools, in effect, to be able to manage this workload. So we use Kubernetes at the moment. we've been using that for a couple of years now. We tried many years ago already to move to Kubernetes, but we found it very difficult at the time, which is how we ended up with Docker on bare metal. But now we've finally managed to get that working all the way up to production. So we now run some strategies and some trading through Kubernetes. We also use a lot of Ansible, which is great for pushing out configuration or doing those kind of sort of repetitive tasks that we would typically maybe have used Bash for, or Bash and SSH. We now run in Ansible because again, it becomes easier to manage the code, and we can check it into a Git repo, and we can pull requests and all that kind of good development stuff. For provisioning VMs, we use Terraform. So Terraform is a HashiCorp product, which lets you basically provision VMs in different cloud environments or virtualization environments. And for example, we use the same Terraform code, also checked into Git, but the same code is used for provisioning VMware and OpenStack without us having to make any changes, so to speak, between going from different environments. We also create a lot of Jenkins ad hoc jobs that our users can run if they want to do some self-service things, and we also use it as a cron scheduler. All the kit we buy at the moment, and all the software we buy as well, one of the main requirements is that it has an API, because without an API, we can't adequately automate the environment. And if we can't do that, then it means that we have to, we would basically need more people to run our environment. So obviously, I'm talking about ThinkLinc today, so that is about delivering a desktop experience to the users, so to speak. And this slide is all about how we got to choosing ThinkLinc, really. So back in the day, we used to use No Machine on Red Hat 5. And when we started implementing CentOS 7, we didn't just switch operating systems, we also switched like the provisioning of or delivery of the actual desktop. So we had some requirements there, of course. It had to be easy to maintain, and it had to be fast and stable. The stable here refers to, like, we had some issues with a lot of VNC servers, for example, where they would work to a degree, and then occasionally, for example, GNOME does some odd X call, a weird X call, and it crashes the VNC server. And we actually found, we tested a whole bunch of VNC servers, and they share a lot of code, so they all had the same bug. And the only one we didn't manage to crash in the end was ThinkLinc. And we also need to be able to reconnect the sessions. So typically our users will run, like, they will be logged on to their desktop environment for maybe a month at a time before we reboot a machine or they reboot a machine. So being able to reconnect your session from either from the office or then going home and work from home for a bit, being able to reconnect to the same session is very important to us. And you can see there on the slide the software we tested. X2Go had a lot of promise, but then in the end we settled for ThinkLinc mainly due to stability issues, and also it has tools around it to let us manage or easily train users to connect to the right place. So why did we choose ThinkLinc then in the end? It's the fastest of the VNC equivalents we tested. Certainly for things like streaming video, it is much faster than a lot of other VNCs. And also the interactive performance is pretty good. It's also the most stable one we found, so we didn't have any random X error crashes. Sendio itself, even before we bought the product, they were really quite quick in responding to our support requests, and they seemed like a nice company to deal with. They all seem to be techie people, which suits us really well. It is possible to automate the install with some caveats, and it was a reasonable cost as well. So obviously we tried all the free options first, but then we realized we might have, if we paid some money, our users would have a slightly better experience. So how do we actually make ThinkLinc available to our users then? Basically, when we build a new server or a virtual server for a user, the typical workflow would be that we boot a server, some Ansible gets run, and then the server becomes available for the user with everything configured. So the way this happens is that we create some Terraform code, which is committed into Git using a job in Jenkins. And the same Jenkins job raises a pull request, and someone verifies the pull request, and then we merge the pull request. And when the pull request is merged, we then have another job that uses Terraform to actually build a server, and it generates some keys and tokens in our HashiCorp Vault and console. So Vault, for example, Vault is a product where you can store passwords, and it does password management for you in a reasonably secure way, or in fact, a very secure way. So anyway, so Terraform builds a server, like it starts the server up, it creates all the disks, etc., and then it boots it up. And on first boot, Ansible will then run automatically, and it will get the credentials we created in the Terraform step and stored in Vault. And it uses that then to be able to run Ansible against itself. So the end result is that it takes about 15 minutes to provision a fully working server from end to end for us in our environment. So when we have a new user, for example, it will take us about 15 minutes to provision a new user for them, or a new server. So in choosing, or in coming up with our solution, and we had obviously some obstacles to overcome. One of the biggest problems was deciding what desktop we should actually support on CentOS or Red Hat 7. So when we went from Red Hat 5 onto the 7 branch, the GNOME desktop got updated to GNOME 3, I suppose it is, because it used to be GNOME 2. And it just looks nothing like what the users were used to. But luckily there is the Mate desktop, which looks a lot more familiar with someone who came from GNOME 2 maybe. So we support both Mate and GNOME, and also XFCE and i3. i3 is a great window manager, even though it is very hard to learn, but once you've learned it, it's great for switching between text consoles. So all us Linux engineers, we all seem to sit in i3 all day. Another big obstacle was to automate the actual install. So we have several environments. All the different hedge funds have slightly different setups, and we had to be able to make ThinkLinc run through Ansible and basically set up the environment correctly for that particular hedge fund and for that particular user. And in the end, we settled on generating an answers type file for the installer. And that then gets piped into the installer at build time, and it basically installs ThinkLinc. Another big problem we came across was user inertia. A lot of people really liked running their Red Hat 5 desktop because they were used to it and they knew where all the things were and they could customize it, etc. So in actual fact, like, the main problems that we came across weren't actually technical. It was more a people problem, getting people to actually switch to CentOS 7. Because we had, well, first of all, there was the UI that was different, but also we had changed the clustering technologies underneath it. For example, we run something called Slurm occasionally, or we used to run Slurm, and we changed Slurm versions and they went onto a different cluster, all the jobs. And that was a bit difficult for users to comprehend to begin with. And actually one interesting thing about ThinkLinc, and actually I think Linux desktops in general, is that a lot of the software is designed in such a way that it redraws large portions of the screen, which works fine if you're on, like, if you have a local workstation and you have a local screen connected to it, everything works great and it looks really nice. However, when it comes to displaying this screen over the network, things or software such as PyCharm and PyDev and Eclipse in particular, they seem to redraw large parts of the screen when they do syntax highlighting, for example, or when someone clicks a menu, the menu, it's quite a heavy operation. So we had to figure out some way of overcoming that, obviously, without, or because otherwise the desktop was too slow to use, basically. And the easiest way to do that was to turn on power saving mode in PyCharm and Eclipse, and that basically disables a lot of the eye candy that you don't really notice anyway, but it also lets you, well, it becomes fast enough to use. So in conclusion then, ThinkLinc allows us to publish desktops to researchers and to all our users as well, with minimal issues. And it's almost as good as having a real Linux workstation, because, for example, you can do multiple monitoring spanning. So if you're at home or you're in the office, or you have multiple monitors, you can span it across all the monitors. You can run in full screen mode. It's like having a Linux desktop locally. The automation is not terribly difficult, and Sendio itself is a small company that is easy to deal with, really. So we are very happy with it at the moment. And that is the end of my presentation. If anyone has any questions, I'm happy to answer them.
Thank you very much, Bilar. We have a couple of questions here, so by the social network. So the first one, what do you mean about reasonable cost?
About what, sorry?
Reasonable cost.
Oh, I see.
No?
So obviously you can run the open source version of ThinkLinc, and it lets you run, I think, 5 concurrent users. But we have about I think 300 ThinkLinc licenses at the moment. And when we compared that to, for example, No Machine and other commercial offerings, it was I mean, it's a much lower cost, really.
Okay. The other question is about the in time for all a small company. What time to implement?
So we've only had a couple of support requests, really. For example, like the GNOME crashed. In fact, actually, so when we first started using ThinkLinc, it also crashed in the same GNOME library that all other VNC servers. And then we spoke to them, and they implemented a fix in a couple of days. And they're really responsive in asking for the right information, and they can I don't know, like, it feels like they can ask you questions at the right level, if that makes sense.
Yes, yes. There are another one. Some users are comfortable with Henschel. It is fine to maintain the change for everybody. Is there something additional we user must learn?
I'm sorry, say again.
Some users are comfortable with Henschel.
Oh, okay, yes, yeah.
Yes.
Yeah.
Is it fine to maintain the change for everybody? Is there something additional we user must learn?
No, so I think, so we used to use Red Hat 5, right? But then when we moved, I think when we used Red Hat 5 as well, I think CentOS maybe wasn't quite as mature, or we had already bought a lot of Red Hat 5 licenses anyway. So when we switched to Red Hat 7 and CentOS 7, we decided to switch to basically CentOS 7 on the Linux desktops. And really, in terms of a user experience, I wouldn't say there's any difference. And especially if you install something like the Mate desktop, it's nice and easy to use.
Okay. So thank you very much, Henrik. It's a pleasure to have here in CARLA 2020. Okay.
Thank you.
Thank you. So, Francisco, it's your time.
Thank you. Thanks, Henrik, for the presentation, for the great presentation. Now, thank you very much for joining us during the first date of CARLA 2020. We invite you to connect again at 2:00 p.m. in the same link of Zoom. We invite you to connect to the High Performance Computing track. Los agradecemos nuevamente por estar conectados durante el primer día de conferencias de CARLA 2020 y los invitamos a conectarse nuevamente a las 2 de la tarde, a las 2 p.m. de la tarde, en el mismo link de Zoom. Los invitamos para que permanezcan conectados y formen parte del track de High Performance Computing. Muchas gracias y los esperamos a las 2 de la tarde por el mismo link.